Okay, welcome to class, everybody. Happy Wednesday. So today we are going to finish up our discussion of equivalence and cloning. And with that, we are going to finish chapter 3 in the book, which was about sort of this intro to data structures, looking at arrays and linked lists. So, and then we're going to move on to more big ideas. We'll start this today on how do we actually rigorously talk about runtimes of algorithms and comparing runtimes of algorithms, which I think is really fun because that's basically a big part of my research. So I'm excited for us to move on to that part. But let's finish up looking at equivalence and cloning where we were last time. So I'm going to go back to our Java code and make sure that I make this big enough. So hopefully I'm going to try to just pick up basically where we left off, but just to kind of hopefully help everyone remember where we were at. So for primitive data types like ints, those hold the actual data of the actual value of the data, and so comparing them, it's very easy. We can just compare what's in that, what's held in the variable, or what's stored there. But for reference data types, like our movies that we have defined, and also like our linked lists, if we just directly compare what is referred to by, say, a variable, a movie type variable, we're going to be comparing memory locations, and so we're not going to get expected results. And so we wrote an equals method for movie, and we actually, the first time we did that, I guided us incorrectly, and I think I had us compare strings using equals equals, which happened to work in this case. But in general, for strings, we should use the equals method on strings so that we make sure that we're actually comparing the value of strings. And I put a message in Discord about kind of some details on that, but basically, for strings, we should use dot equals. So we've got we can add an equals method for our movie class, where we're just comparing, is the name of the movie the same and is the year the same? Yep, that means they're equal. We also started to write a singly linked list equals method, and that's where we kind of saw, we tried to compare their two strings, but just to finish off with equality, I just want to look at the method that's already written in the, on the website. So I'm just going to copy that over, and we can just kind of look at that line by line, make sure that we understand. Let's see. Great. So, okay, so our goal, what we want to do is be able to call, I have some singly linked list. Let's see. And I've defined S1 to be BZN and then followed by SLC. And similarly, I've defined ST to be BZN followed by SLC. So these two are right here. And I want to make this equals method work. When I say S1.equals and I pass in S2, in this case, they should be true, right? This should be true because these should equal each other. So I'll just run this, and we can see, we can already confirm, okay, great, that equals method does seem to be working. These should be equal, right? So now let's take a look at it. Okay, so first, we can just make a quick check. So we're passing in another singly linked list. Okay, do they have the same size? If not, then we should return false, right? That makes sense. Definitely not equal in that case. Otherwise, what we need to do is we need to walk over the two lists and compare, what they are,
Don't you need brackets when you return false statements?
So I always write my if statements like this, just kind of out of habit. But in Java, you actually only need the brackets if there's more than one statement. So the book will often do that, omit those brackets. But if there were two things that I had to do here, like for some reason I both had to, first I needed to, like I don't need to do this, but say I wanted to print out something, like I wanted to print this, then I would need the brackets because there's two statements in this code block. But when there's only one, I can omit them. So yeah, thanks for that question, because I personally just always put in the brackets, but makes the file a little longer. Less good for our tiny screen in this room for some reason that we have. Yeah, cool. Any other questions so far? Kind of just been charging ahead on what we did last time. So how do we implement this walking over our two singly linked lists? Well, we need two node objects, one for this linked list that I'm working on right now, and one for the other one that we passed in, so walk A and walk P. And then I'm just going to walk over those and check. Oh, unfortunately, this is pretty long. Let's see if I can make that any smaller. See, here's where we don't even want to be short. I'll put this here. Yeah, I don't need those brackets, but so as we're walking along, if these elements are not equal, so I got to call my equals method on the element from A and pass in the element from B. So if those are not equal, then I should return false. These two singly linked lists are not equal. Otherwise, I just continue. And if we make it all the way to the end, then they must have been equal the whole way through, right? I've walked over my whole list. They must be equal. Yeah?
Maybe I'm just forgetting, but aren't we working with the dot equals methods? How can we call it within the same method?
That's a really good question. So why can we call dot equals on, like, is this not sort of circular, is what you're saying? Anyone have any thoughts? And yeah, that's a really good question. But there is a solution. Yeah. Yeah, exactly. So once my sort of order of operations here is that, or, if I kind of break this down, so walk A is a node. We call get element on it. So at this point, the data type, the type of this thing, like I could put parentheses here, for example, if I wanted to, but I don't need to. But the data type inside the parentheses is whatever the data type of my node's element is. And in our implementation, our node's elements, let's see, what are their strings. And in general, they could have been generic. Like the way this would be circular if my nodes were linked lists, or my elements in my nodes were linked lists. But yeah, but in this case, they're strings, so thank you.
So we're using like the built-in string not equals method then?
Exactly. Yep. And yeah, so equals, it's a special method because we want to define equality, but each object is going to have its own implementation of what is the equals method. And so here we're calling dot equals for strings the same way that we called, like we actually are calling this, I just jumped over to movie. So in our movie equals method, we also used the string equals between the names, right? So our movie.getName is a string, then we call the equals method on that string name, and so we're calling it there as well. So yes, calling equals methods of other objects is highly encouraged inside your equals methods. Cool. And I don't think we should have made any changes. Great. So that will be our discussion of equivalence for now. But relatedly, now I want to talk about cloning, because cloning and equality, we're going to have to deal with some of the same ideas. So you may remember, I can't remember, so we're going to move on to cloning. So here we are, moving on to cloning. So if I look back up to when we were defining our movies, so on this line 20, I make a movie M3 by assigning the variable M3 to be M1. And so we saw that these M1 and M3, they're both pointing to the same object. And so when I print out, so maybe I'll actually put this down here. So just remember M1 and M3 point to the same object. And so when we do this equals, here, I'm going to run this. Can anyone tell me, why do I get true here when I do equals? Yeah.
Because it's pointing to the memory location.
Yeah, exactly. It's like there's M3 and M1 and M3 both point to the same thing, so we get that those are the same. Even though they actually happen to be, that's why they're the same. So, but this means that we haven't really made a copy. Like M3 is not really a separate copy of this movie, right? It's just pointing to the same thing. So, for example, if I do something like, I think my movie class does not have a set year yet. So I'm going to add public void set year. And, I got to take in a year, huh? I'm going to take in a year, and I'm going to set my year in my movie to whatever I pass in. So now I have a set year, and so I'm going to try this out on M3. So M3.setYear, and it was 2001. I'm going to change it to 2022. So M3, if I look back, should be, it's a movie, it's Harry Potter and the Sorcerer's Stone, and it was 2001. And so I'm calling on M3 set year, but now if I print out M1.getYear, oh, did I not make this? Oh, funny. Okay. So I'm just changing my get year to be capital to be more consistent with our sort of Java. Is this not? I just haven't saved. So I just haven't saved this yet. So, okay. Movies have a set year and a get year. So now, okay. So I'm calling get year on M1, right? And that's strange. What? Oh, I must have called it up here with a get here. What? My guess is that, in my equals, I called get year with lowercase y. Okay, so I called on M1, like I set year on M3, but now M1 is also changed. And that's because they're pointing to the same object. So if instead of M1 and M3 pointing to the same object, I want them to point to different objects, what I want to do is clone, I want to be able to copy a movie, right? And right now, I actually don't really have any way to do that. So, for a couple minutes, I'm going to let you all think about how you would write a clone method. So what's this going to look like? So I want to make M4, a movie M4, and I want to assign that to be M1.clone. So it's going to be a copy of M1. And so I bet that you can do this in just one line, but you do need to specify, what does this method look like? But I bet the code of it can just be one single line. So I'll give you a couple minutes to think about this. Feel free to turn to a partner and turn to a neighbor and talk about it. If you're lost, if you think you know how to do it, feel free to talk to a partner. But I'll just give you a couple minutes to think about that. Okay, wherever you are on this, turn to a neighbor, multiple neighbors, and what is this method header look like? What do we take in? What do we return? And also, what is the code in the method? So, turn to a neighbor, see if you know one of those. You can do it. It's not too scary.
Yeah, no, I thought it was that, but it's not.
Okay, if you're not talking to a neighbor, you gotta do it. As hard as it is.
Yeah, definitely should. This is
Okay, great. Anybody want to tell me what I guess maybe we call this the method signature. I'm not entirely sure what the correct term is there, but, you know. Any pair willing to tell me what they think this method signature should look like? Sure.
Public movie clone.
Yeah. So from our this example here, we see that when we call clone, it needs to return a movie, and so that's why we're returning a movie here. It's not taking in anything, and we'd like this to be public, so it can be used in general on movies. So, great. And could another pair tell me what we should do inside this method? Yeah.
Return new
Yeah, exactly. So all we need to do is we're actually creating a new movie here, and we're giving it the name of our movie, the year of our movie. We're returning it, and that's going to work great. So now, just to show that, okay, it runs, that's awesome. But now, okay, so before, so let's contrast. So we made M3 like this, just by using the assignment operator. We're making M4 using our clone method. And now, we saw that if we changed M3's year, we changed M1's year too. But now let me change M4's year, M4.setYear, and let me, okay, this is going to be in the future, 2050, but now if I print out M1's year, it's still going to be 2022 because we actually made a copy of the movie. Cool. Any questions about that? Yeah.
Does the quality operator, before you set the other year, does it return true or false?
That's a really good question. So you're saying if we do this, and I say is M4 equals M1, so what do you think?
Well, we also have to comment out the set year because we changed that. Or
Yeah, we can do that.
maybe not.
Yeah, let's. You're right that makes it a little easier to wrap our heads around, regardless. So yeah, let's say we did comment that out. What do you think?
I'm gonna say no because it's a new object.
Yeah, exactly. Like if we drew the picture, and maybe no, that didn't work. Maybe I can draw the picture. Yeah, I can draw the picture. So when we made our clone, we said, okay, we got M1 here. It's pointing to some movie, Harry Potter, whatever. Say it's even 2022, it doesn't matter. M3 was pointing to it, but now M4 is pointing to, we copied these over, but they're new. It's pointing to a new movie object. Cool. Great. Okay, yeah, we're looking great on time. Any questions before we wrap up cloning and equivalence? Yeah.
So, it's clone, but I'm confused on why it says with insane. They are clone.
Oh yeah. Did I say sorry. You said true? Oh, okay, great. Yeah. I realized maybe I didn't even listen to you. Yeah, no. Thank you. No, it should be false because of this picture, right? So M4 is if we really think about our computer, what's happening in our computer is in binary or whatever, in circuits, there's this new place where this data is stored. And M4 gives us a pointer into that. It gives us a way to access that data. But we made new data for it, and it's pointing at that new data. Versus when we made M3, we didn't make any new data. We just made another variable that refers to the same thing. Yeah, and definitely, I mean, I think it's a difficult concept, but it's going to help so much in programming and your whole computer science career. Yeah.
Is there any time we want to do more pointers to the same object?
Well, that's a good question. What was that?
Static objects. Doesn't
I
that always point to the same thing?
I'm not sure. Well, I mean, you may. Let's see. I mean, nothing's really coming to my mind right now, but one last thing I'll leave us with that, and yeah, maybe I'll try to post something on Discord about that, or maybe as I explain this next thing, there'll be an example. But so you may have noticed, like, okay, we did something very simple with movie. We just returned the name and the year, but remember, strings are actually reference data types, right? So in a way, we kind of swept under the rug some details here, because it makes sense that we actually made a full clone with an int. Like, that's a primitive data type. It's actually just we're just passing the value around. But we've been saying that, strings they're reference data types. Like, isn't this actually just a reference to that string name? But basically, Java strings are a little bit complicated, and I feel like sometimes they feel like objects, sometimes they feel like primitives. So in this case, it works. But there is this concept of shallow clones and deep clones. And so a shallow clone is where for all, let's say, we have a linked list, and its elements are objects. Like, it's a linked list of movies. So if I say that I'm making a shallow clone of that linked list, then I would say that I'm making my linked list variable, like I have list 1 and list 2. List 1 and list 2 should point to different things. So let's go to my picture. List 1 should point to something different from list 2. But inside those lists, there are nodes. Don't know why I made them circles this time instead of squares, but then inside of the nodes, those actually all point to the same objects. So my first element in each of my lists points to the same object. And so if I make a change to object 1, then it's like list 1 changed and list 2 changed, even though they're different objects. So there's kind of another layer of this. I don't think that we're going to have to deal with it in this class, but I did want to mention it, just kind of feel like, oh, there's a big world out there. So we call that a shallow clone. Now, if instead, when I made my lists, I copied over all my reference data types. So object 1 would be here. Object 1 would have been copied over here. That we would call a deep clone. So, something else that is in the book you can look at more, and I'll discuss if it comes up. But cool. Great. So for the rest of class today, we are going to move on to starting our analysis of algorithms, talking about runtimes. So I think I put this in, let's, oh, I'm not there, huh? Select this, trash. Oh, this one, also trash. Great. Okay. So again, I'm going to use some slides from the book and also some slides from Dan DeFrance, who has taught this in the class. So moving on, Chapter 4, Analysis of Algorithms. As a sort of warm-up because our goal is going to be to talk about how do we rigorously define runtimes of algorithms. So as a warm-up, I will tell a story of the mathematician Gauss. So apparently, when Gauss was like 10 years old or something, he's in school, and this is in like the 1700s, and his teacher wants everybody in the class to like take some time, like the teacher wants some time for themselves. So the teacher says, add up all the numbers from 1 to 100, thinking that this is going to take a long time, right? You know, you got to add 1 plus 2 is 3. Okay, 3 plus 3 is 6, etc. And okay, that's going to take a long time. But clever young Gauss notices that, wait a second, I don't have to do all those steps. I can just notice that, okay, if I pair 1 and n together, I get n plus 1. And if I pair 2 and n minus 1 together, I also get n plus 1. And if I pair 3 and n minus 2 together, I also get n plus 1, right? Does that make sense? Like, why is it that if I pair 3 and n minus 2 together, I get n plus 1? Anybody want to tell me? Is n plus 1. Great, exactly. So that's what we're doing with all of those. We're just noticing that this is true. And so, also, has anyone heard this story about Gauss? Okay, I got a nod, got another hand. Okay, well, so we notice that we don't actually have to add all these up. We can just take all those n plus 1s. So we had a bunch of n plus 1s. And since we were pairing all of our elements, we have a total of n over 2 of them, right? That's what this n over 2 is doing. So I can really just make this one calculation, and I can add up any amount of numbers that I want. And I just need to do this one calculation. And so if we think of these two things as algorithms, like I've got algorithm 1 is to just add all of them together. And algorithm 2 is I just compute this number. Those are different algorithms, and they give me the same output. They're going to give me the right answer every time, right? It's not like one's wrong and one's right, but there is something different about them. And, so there's our formula, and I would say that the big difference is their running time. And so before we get into formally defining this, I wanted to open it up and ask, like, what does running time, how would you think to define running time? Even if you've never thought about it before, like, what comes to your mind inspired by this example? Any thoughts? Yeah. Yeah, so, okay. Great. It's like, how long does it take? But what about if we start thinking about like different inputs? Like if I ask you to, so these two algorithms, we'll call, so this one we'll call Gauss's way, and I stole these slides from Dan de France, and he called this Ludwig's way because I think this was like a general German student. Might be named Ludwig. So Ludwig is the one who's just sitting here adding them all up. But the point is, if I ask you to add up all the numbers from 1 to 1, Gauss and Ludwig, it takes them the same number of steps, right? It takes exactly the same amount of time. In fact, like it might even take, like Gauss has to define like what is n plus 1, have to divide by 2. Like it almost feels like that takes longer for that really small input. So maybe I'm going to say this depends on the input. Cool. Anything else come to mind or things you've seen? Yeah.
On the user end, it's more like the total time, but usually computer science are more involved, like kind of like the limit, like the long run form of the time, like whether it's
Yeah.
or exponential.
Yeah, that's a good point. Like as a user, I actually only care about like my input. Like when I run it, I really care just about that. But it's true. As computer scientists, we want some overall, some general trend that we'll call. One way that we can say that is the asymptotic runtime. So yeah, I like that though. The user just cares about their input, but in CS we care about a like general categorization. Okay, yeah. Yeah, so a really like basic way, and actually the foundation of the sort of theoretical way of analyzing runtime is to look at the number of steps. And yeah, I mean, basically the underlying model is to kind of consider every step to just take the same amount of time. Like it doesn't matter if I'm accessing an element of an array, or if I'm adding two numbers together, or if I am dividing two numbers. Those all are just a step. And so then I get to kind of think at a higher level, how many steps does it take? Yeah. Cool. Looks like I got space for one more bullet point. Anyone who hasn't spoken yet have any thoughts? What does runtime like make you think of? Yeah. Yeah, and then I guess, so I just said, okay, we have these basic steps, but so we have our numbers of steps, which are basic steps, but then we also have operations that might be less basic. And so that's going to let us think even higher level. You know, by the end of this class, like it would be really awesome if we can analyze an algorithm and we can say, well, it's got a step that sorts, and then it's got a step that walks over that array that we sorted, and so now I don't have to think about any of the details of the sorting. I just know that the best sorting algorithm is going to take n log n. Walking over the array takes n, so I know it's n log n, and I don't have to think about any details. So being able to step up to a higher level and think about operations or functions that are less basic is going to be really helpful to us. Cool. So thank you for participating in that. So great. One thing that we didn't touch on yet is that one logical thing to think about when we're thinking about runtime is that we want the average case runtime. Like on average, if I'm just a user of a program, I want you to tell me what the average runtime is. But that's actually really hard to define, because in order to do an average runtime, we're going to need a distribution over the probabilities of the inputs. And even in a really controlled setting, that can be hard to define. So instead of the average case, we usually focus on the worst case. So any thoughts, like why is worst case at least like something reasonable to do? What guarantees does worst case get us? Yeah.
You know, when your program is taking too long, or you can tell us like how long this is going to take. So I guess what I'm trying to say is that you know the worst case, you know at most.
Yeah, exactly. I mean, it's kind of like, maybe it's already there in the name, but you know, it does give you some information. It tells you what is the absolute most time that this could take. And sometimes you actually really do care about the very worst case, because you don't want you're like, well, I'm okay with my person using my website waiting this many milliseconds for it to load, but I'm not okay with them waiting like 2 minutes. And so knowing that I'm in the millisecond range is actually useful. Yeah.
Would you also want to know, I guess, the least amount of time it can take? Because if you're, say, like you're sorting something, checking, all of the elements are already arranged, you don't want to rearrange them algorithm.
Yeah. I think that's a really good thought. And I think when we are trying to understand the runtime of an algorithm, it is really good to understand the best case. When it comes to, usually the best case is like very fast. And so usually we actually don't really worry too much about like doing something special in the best case, because it's like, well, we still have to walk over our input, and the algorithm's not going to perform too badly in the best case. But I do think like understanding the best case is really important. Yeah.
I would say best case is to really accurate because there's a lot of tricks. Like you list of 10 or a million will give you almost the same best case time for grabbing a random element, grabbing an element,
Yeah.
so it will be a time for your input size.
Yeah. Cool. So a important idea as we are formalizing our analysis of algorithms is going to be these sort of touchstone functions that we can compare our algorithm runtime to. And so the sort of names here, top left, we have a constant function. And I guess just to make sure that sort of this notation isn't tripping us up, so g of n is a function taking an n, which is representing the input size, and it's saying, okay, what is the runtime, or actually more accurately, how many steps do we take given that our input size was n? And so if it takes us just basically one step or a constant number of steps, then we're going to say that it is constant time. I can think of 3 examples of constant time algorithms that we've seen recently. Anybody have ideas of things that are constant time that we have been talking about today or recently? What was that? Yeah, assignment, especially like just assignment is a constant time operation, definitely. What about even like full algorithms that are solving problems? Yeah.
Just getting the element of an array,
Yeah, exactly. Getting an element of an array is like a classic constant time operation. We're able to just go grab that element. But even algorithms can be constant time. So we saw, like, what about Gauss? It's not really just one, but we would eventually, we'll see how we call this how we would consider this a constant time algorithm, because it's only making it's doing addition, it's doing multiplication, it's doing division. So it's really only doing 3 steps. No matter how big my input is, it's only doing 3 steps. And we'll see how we can formally say that. But it's only doing 3 steps, so we would call this a constant time algorithm. Another thing that's constant time is deleting the first node in a linked list, because all we have to do is update that head node, right? So, great. Let's see, things like n squared, n to the third, I assume those are probably pretty familiar, from math class. You might feel a little less comfortable with log functions, but in computer science, log is extremely important. And similarly, exponential functions, I think hopefully in this class, but definitely as you keep going, you're going to get really comfortable with exponential functions, really comfortable with log functions. So these are our 1, 2, 3, 4, 5, 6, 7 sort of touchstone functions that are going to be the basis of our runtime analysis. Okay, so before we get to our formal analysis of algorithms based on their worst case runtime, it's also important to acknowledge that actually running experiments is a good way, a reasonable way to compare algorithms as well. You're doing this in your lab, right? You're comparing different methods from your array data structure to methods of your linked list data structure, or between their methods as well. And so if we were to look at an implementation of this was the just add all your numbers together to add from 1 to 100 or from 1 to n versus Gauss's way, where we just return this mathematical expression, evaluate it, and we can compare these by just running them on a variety of inputs. So that's what we're doing in project 3. And so, yeah, you can see we can use some built-in timing function. That's all nice. But in the end, this is going to have some limitations. I think this first one might kind of seem silly to you that this is a limitation, because what have we been doing so far? We are implementing algorithms, right? We're writing code. And it might kind of feel weird to say, well, if you run an experiment, you have to write some code. And you're like, well, that's the whole point. But really, in a lot of cases, it's a lot easier to actually analyze the runtime of an algorithm than it is to implement it. And so if you are trying to make a decision, again, thinking of our website, where we want to make sure that our users are only waiting milliseconds or some amount of time that they can't tell how long it's been while our website loads, and I know that I have 2 potential algorithms for, I need to tell them they're making a search, and I want this to go fast. If I can just think about an algorithm and know that it's going to run in n² time versus another algorithm and it's going to be faster, I don't need to implement those and test them. I can just analyze them on paper. Additionally, we can't really include all possible inputs, and so experiments will fail in that case. And then also, it's really going to matter what computer I use and what software I use to implement them. So these are all limitations of experiments, and so next time we'll see what can we do better than just experiments, how can we formalize this analysis of algorithms. And that is all for today.